Electric storms Hamburg. Problem 1. We get an electric field in free space expressed as E equals to 5c squared over epsilon 0 at the AC direction, volts meters. Now, this AC direction is exactly the same at saying K, which is up and down along the axis C. And voltmeters, it's the same as saying Newton's coulomb. So we're talking about electric fields. The problem is asking me to find the total charge contained within a cube centered at the origin of 4 meters side length, in which all sides are parallel to a coordinate axis and therefore each side intersect an axis at plus minus 2. What is that saying? Well, that's saying that we will have to analyze what's going to be the enclosed charge by a cubic geometry. And a specific cubic geometry that we know it's going to have 4 meter side. Copy, paste. It's going to be our cube. My cube, and it goes like that. I just grab it, paste it all together, and we can manipulate it. Now, this cube is going to be centered at the origin, something like this. Now, this is not necessarily a scale. I'm going to make it a little bit higher, a little bit bigger, so we can work with it. Take this to the back. And this is going to be centered somehow here. That's my cube. Probably a little bit thicker lines would help a lot. Oops. Talking about this one. These will need thicker lines. Alright, that's our cube. So our cube is going to be centered at the origin, somehow like this, right there. There we go. Now it looks more like a cube. And it's going to be intersecting different sides. We know that side to side is going to be having 4 meters. Here we will have 4 meters. Here we will have 4 meters as specified by the problem. Then I think we can erase this thing. Center at the origin right here, and we got C-axis going this way. We have X-axis going this way. We have Y-axis going this way. So that's the representation of our geometry we're going to analyze. What else? We know there's going to be one electric field that's going into K direction. That means this electric field is going up, and we'll have this dependency on the C value. That means if we analyze in here, which has a specific C, our value of electric field is going to be different than if we analyze in here, which clearly is a lower or smaller C, or actually in a negative fashion. So let's try to see what's going on. We know that for Gauss law, we need to see what's the total flux going perpendicular to every side of our geometry that we want to enclose the charge. If we know the electric flux, it's going up in the k direction. That means that the only walls or the only sides of the cube that are actually creating a perpendicular like this position, it's going to be the upper side and it's going to be the lower side. For the upper side, we know that the electric flux is going up. That means it's going out of the surface. For the lower section or electric field, it's going up. That means it's going inside the surface. So we will not have to analyze all the sides of the cube, since the rest of the sides, the front, back, side, left, and side, right, actually they are parallel to the electric flux. So no need to analyze. And we can consider something else. We can consider the positions of these two elements. For example, the position for this side, we can say that it's located at C equals 2. The position of this side, since it is centered at the center at the origin and it has a 4 meters length on each of the corners, we can say it's located at C equals 2 minus 2. That's going to be helpful. What else? We know that for a cube or the side of a cube, we will have a differential surface element for each side. If we're working with the upper side, which is parallel to the x and y plane, the differential element for this surface is going to be dx dy. And we're going to consider this positive because we are in the upper section, we are in a positive c. For this one right here, we will have also a differential surface that's parallel also to the x and y plane. However, since we are working in a lower section, we'll consider this to be minus dx dy. Why is this important? If we recall the Gauss law, which states that the flux equals to the charge equals to the closed surface integration of g dot product ds. If we get several parts of surfaces that we have to integrate, we're going to divide this integration in as many sides we're analyzing. In this case, we got two sides, so flux equals charge equals to surface integration. Surface 1, surface 2, there's going to be d ds1, integration of d ds2. Here, this ds will correspond to this one. This ds will correspond to this one, right there. What about the value of the flux density? There is another theorem that states that flux density equals to epsilon zero electric field. If we go by that theorem, we will see that epsilon zero times the electric field, which is 5c squared over epsilon zero into the k direction voltmeters. That means epsilon 0 and epsilon 0 go away, and we end up with a flux density equals to 5 c squared into the k direction volts meters. This is going to be the one flux density we're going to integrate. We're going to replace in these two values. So we have already the flux densities. We have already this differential surface elements. We can go and analyze the problem and replace the values. So the first one is going to be a surface integration. That means a double integration of t, but d equals to 5 c cubed, square ds1, which is the x dy, plus double integration of 5c square of the d surface 2, which is minus dx dy. And here, this double integration represents integration about x, integration about y, integration about x, and integration about y. From where to where? If we get sides of 4 meters length, we can go minus 2 to 2 or 0 to 4. However, since it is actually located at the center, to obtain a total of 4 length on each direction, we will have from minus 2 on 2, minus 2 on 2. This one, minus 2 on 2, minus 2 on 2 for the x and y on each. They seem to be the same, and they pretty much are. However, there is one small difference: the location of each surface. This surface right here is located in the upper section. That means we work with a c equals on 2. So we replace 2 square. This surface located in the lower section. That means we got a c of minus 2. We replace minus 2 square. By the characteristic of the electric field, this will not affect at all, since minus 2 square and 2 square are actually the same. So we integrate. Since all this together, it's actually constant, it can go out of the equation. This one too, constant, can go out of the equation, and we will integrate about dx and dy in both. So we will have an answer of 5 times 2 squared, which is 4, dx dy integrated, that means x, y evaluated, minus 2 on 2, minus 2 on 2. This one, exactly the same, with a slight difference. Here we got a minus sign. That means we will have minus 5 times 4 times x, y, evaluated from minus 2 on 2, minus 2 on 2. We can take this out, and here these two elements are clearly the same magnitude, only one has a negative sign. That means the answer is going to be 0. We're looking for the total charge, so we can say that the total enclosed charge is going to be 0 coulombs.